Okay, today we're going to look at alternate units of concentration. There are four that I would like you to become familiar with. Of course, we know molarity. We're going to look at parts per million, parts per billion, and grams per 100 milliliters. You see this not so much in chemistry books, but you do see it in the pharmaceutical industry and maybe even in a pharmacy, because not everyone has been trained in chemistry, and this is something that most people can understand without any formal training. In fact, you'll very often see this on the ingredients list on the side of a packaging material. So the first one we're familiar with is molarity. It's a measure of concentration stated in units of moles of solute dissolved in liters of solution. Sometimes concentration is expressed with alternate units of concentration, as we said earlier, such as grams per 100 mLs of solution. And I'll give you a brief example. The protein drink contains 12 grams of whey protein per 100 mLs of solution. So that would allow you to determine how much protein drink to drink in a day. When a solute is present in very low and extremely low concentrations, then it is customary to use parts per million and parts per billion as a unit. Parts per million, by definition, is the concentration of a solution in grams of solute per 1,000,000 grams of solution, which can also translate to milligrams of solute per liter of solution, because the density of water is 1.0 grams per milliliter. We're going to assume that the density of water is 1, very close, and it is very close to 1. Here's an example that we can use to show all the four different ways. 50 grams of table sugar, which has the formula C12H22O11, basically two glucose molecules stuck together with a water molecule removed to form the bond, and is dissolved in an Olympic-sized swimming pool with dimensions of 25 by 2 by 50 meters. State the concentration of sucrose using molarity, grams per 100 ml, parts per million, and parts per billion. And let's assume that the density of water is 1 gram per centimeter cubed. So we continue on to the next board, where we see that the first step is to calculate how much water we have. So 25 by 2 by 50 gives us a volume of 2,500 meters cubed of water. Well, every meter cubed has 1,000 liters in it. You can say, and to prove it to yourself, you could look at the fact that 10 decimeters are in 1 meter. And if you cube that conversion factor, it will give you the cubic conversion factor from decimeters cubed to meters cubed, and the decimeter cubed also corresponds to a liter. So 1,000 liters are in 1 meter cubed, and then there's also 1,000 grams of water per liter of water, based on that density assumption we made. And so the total is 2.5 times 10 to the 9 grams of water in that Olympic swimming pool. 2.5 billion grams of water. The first step, the molarity calculation, which involves moles of solid over liters of solution, requires us to calculate how many moles of the sugar are present. So here's the number of grams divided by its molar mass: 12 carbon atoms, 22 hydrogen atoms, 11 oxygen atoms. We have 0.14 moles of sugar dissolved in 2.56 million liters. So I took a step back, right? It's that many liters of water. And if you multiply by 1,000, you get grams. So the concentration comes out to be 5.84 times 10 to the minus 8 molar. Pretty straightforward for those of you who are familiar with chemistry. In the grams per 100 ml units, we know that there's 50 grams and 2.5 billion milliliters. Therefore, let's set up a proportionality where we have X grams per 100 milliliters. So we simply just set it up like a fraction. This is like the fraction that's in higher terms. Let's say we had 3 over 9 here, and we're saying it's equal to something over 3, a smaller number. Well, we all know it's 1 over 3. But the difference in these two fractions, the denominators are way different. And now what we do to solve for the value of x is we cross multiply and then rearrange to find x. So 50 times 100 is equal to 2.5 billion x. X equals 5,000 over 2.5 billion. So there are 2.0 times 10 to the minus 6 grams per 100 ml. So you likely would not taste any sweetness in the water if you were to take a drink of it. So now let's move to the types of measurement that are more appropriate for really low concentration substances, like parts per million and parts per billion. In parts per million, 50 grams of the sucrose is dissolved in 2.5 billion grams of water. But we want to find out how much sucrose is in 1 million grams of water, because it's a part per million. So we're going to do the same thing as we did here, turn it into a fraction. X over 1 million is in the same proportion as 50 over 2.5 billion. Solve for X, and we get that it's 2.0 times 10 to the minus 2 parts per million. So because we're still getting a fraction, it's perhaps more appropriate to go to parts per billion. Because we'd like to get a number that's bigger than 1 when we have the right unit. So we know that parts per billion is 1,000 times less concentrated than parts per million. So all I did was I multiplied by a conversion factor. We have 2.0 times 10 to the minus 2 parts per million times 1,000 parts per billion per 1 part per million. And the result is our concentration is 20 parts per billion. A very low concentration indeed. You might think, well, what's the use of having such low units of concentration? There are hormones and gonadotropins, which are hormones that control hormones within the human body, that would probably work around those concentration levels. So those kind of measurements are useful to people like biochemists and pharmacists, people with medical applications of chemistry. Here we have a simple question just that's designed to test your ability as you're supposed to have gained it by now. The curriculum calls us for us to know how to make dilute solutions, or how to dilute solutions, or how to calculate the concentrations in titration. So consider this a review. The first question I ask, how much aluminum acetate do you need to make 500 mLs of a 5.044 molar solution? So we recall that the molarity of the solution times its volume is going to give you the number of moles, because you'll see that the units are moles per liter for molarity. The volume is in liters, so the answer is going to allow you to cancel liters, and the answer will be in moles. So we have the molarity of the solution, we know the volume of the solution, so the number of moles of aluminum acetate we need is 2.522. Now if you know the number of moles, you multiply by the molar mass to find out the number of grams, because moles times grams per mole, which is the units of molar mass, when you cancel moles, you get an answer in grams. That's what we're doing right here. So here's the molar mass of aluminum acetate. Remember, aluminum has a positive 3 charge. The acetate anion is minus 1, so you need 3 acetate anions to combine with the aluminum cation to form the neutral compound. Here's the mass of aluminum, mass of carbon times 6, because there's 2 carbon atoms, and that 3 means 3 times 2. There's 3 hydrogen atoms in acetate, but there's 3 of them, so you get 9 times the mass of hydrogen. There's 2 oxygen atoms, and you again multiply by 3 here in the bracket, so 6 oxygen atoms. Here's the molar mass of aluminum acetate multiplied by the number of moles. So this number times the number you would get by finding these out, by adding them together, multiplied will give you 514. Because we only had 3 significant figures here, I rounded it up to 515. Now, suppose you want to make the same solution as above, 5.044 molar, from a stock solution containing 8.54 molar concentration of aluminum acetate. And now, if you need 350.4 mLs of it, how much stock solution will you use? Well, in this one, it's a dilution. So the initial number of moles, N1, is equal to the same number of moles after the dilution. You still have the same amount of aluminum acetate in solution. All you've done is added some solvent. So if you know what your concentration has to be after you finish diluting, I should have switched it around, should have made it V2, but it doesn't matter, you still get the right number. Here's your stock solution. Wait a minute. Somebody changed the number here, I'm afraid. I'm going to double check this. This number doesn't look like the original number I had here. Your final concentration, yeah, you need 5.04 molar concentration, and you need 350 mLs of it. and you're starting off with 8.54, yeah, that's what happened, it got erased. It was 8.54. So to find V1 is what you need, how much you need of the original solution to produce this much of the diluted solution. So we set up the dilution equation, we transpose the value of M1 to find V1, and we get 0.2069 meters, which when you multiply by 1,000 gives you 207 milliliters when you account for the significant figures. You're only allowed 3 from the original question. The next question I want us to look at is a review of how to write molecular equations, ionic equations, and net ionic equations. Wheel it this way. And do not turn it on. All combined.